The physical quantity that measures how effective a device is at inducing an EMF by changing magnetic flux is called inductance. This is just a measure of how good a device is at Faraday's law of induction. The practical applications of inductance include transformers, heating coils for dryers, camera flashes, and more. Mutual inductance measures the effective induction of one device onto a second device. It is represented by the capital letter M. The transformers explained in the previous section are examples of mutual inductance. The primary coil transfers energy through induction to the secondary coil. You can see in the diagram that a current is induced in coil 2 when the current is changing in coil 1. The inductance measures the effectiveness of this coupling between them. Remember, the formula for Faraday induction is dependent on angle theta and current B. If geometry is fixed, then we can assume that theta does not change, and the magnetic flux will be dependent on the change in current. This means that if the current changes in coil 1, then an EMF is induced in coil 2. The equation for EMF in the second coil will be the negative mutual inductance times the current change divided by the time over which it changes. The negative sign on the mutual inductance quantity means that the induced EMF of coil 2 will oppose the change in current of coil 1, consistent with Lenz's law. It also turns out that mutual inductiveness runs backwards with the same effectiveness as it runs forwards, meaning that coil 2 will induce a current on coil 1. The equation is essentially the same as the first. In some devices, a large M is problematic. As a result, many appliances that make use of this principle of mutual inductance reduce M. An example of this is a heating coil for a dryer. You can reduce M by counter-winding the coils as shown in the figure. You can see that the wires are wound so that each consecutive coil has the opposite magnetic field than the previous coil. This allows their respective magnetic fields to cancel, which will reduce M. Not only can a coil induce a current in another coil, it also induces a current in itself. This is known as self-inductance, represented by a capital L. It is shown in a circuit as 3 small humps. Self-inductance means that when current is changing in a coil, not only will it induce an opposing current in an adjacent coil, but it will also induce an opposing current in itself. The equation for the EMF generated through self-inductance is negative L times the change in current divided by the time it takes to change. A greater self-inductance means there will be a greater opposition to changes in current. A large self-inductance, or L, can create many problems for smaller devices, but there are some uses for it, usually having to do with storing the self-induced charge. An example is the camera flash circuit shown below. Flashes use an oscillator to switch a battery on and off in order to induce a self-induced current. This charge is stored by a capacitor and released when the flash is needed. More oscillations means more stored voltage. It is possible to calculate self-inductance if you know the geometry of the magnetic field. As you can see, this becomes very complex, and so it is usually a given quantity. Luckily, we don't have to worry about this. Because a solenoid has a very simple magnetic geometry and shape, we can calculate its self-inductance using the formula shown. This equation shows that self-inductance depends on how effective current is at creating magnetic flux. An alternative way of looking at the opposition EMF created by induction is to look through the lens of energy. Energy is stored in magnetic fields. This energy takes time to build up and also to deplete. This helps explain why rapid changes are opposed in inductance. The equation for the energy of inductance can be derived as 1/2 times the self-inductance times the current squared as shown. Note that this equation is similar to the equation for determining energy stored in a capacitor. Thanks for listening.